Okay, so welcome to the peer-to-peer lecture, to the exercise today. I want to present you and with you go through the fourth exercise sheet. And, in this exercise we will have a look onto our simulations. We will simulate chord, pastry, and a simple overlay we created in this exercise, and we'll discuss your solution maybe. So the first task was to visualize chord in perfectsim.com in the simulator, and it was a very easy task just to visualize the chord config file given here in the visualizations folder, and your task was to describe the meanings of the global network positioning. So, is there anyone who wants to present his or her results? Okay, no one. Okay, then let's go through it. So as we heard in the lecture, GNP stands here for Global Network Positioning. More or less it is a technique to describe the delay between two or many other systems in the network, especially between the nodes. So if messages are sent around, we want to calculate somehow a delay for the messages which are sent around, and for this we use network or positions in the network, or positions in a we consider coordinates to calculate the distance between two nodes and therefore to calculate the delay. So, and if you then start the simulator, you have two different kinds of views in the simulator. Here I have some screenshots. Okay, first you can have you can visualize the GNP coordinates. So here the nodes are ordered according to these coordinates and have certain distances on a 2D, two-dimensional plane. And, if we consider the other visualization tool, we can have the nodes ordered on a chord ring according to their IDs in the network. And, as we told before in the last lecture, we have here the nodes in the network, we have the successors, the predecessors of the nodes, and we have the finger here, the gray arrows you can see in the picture. Were there any problems, any annotations? You want to add something? Okay, then we maybe should just go through this. The next task was then to inspect the simulation results. So in order to gain more insights into the simulator. Especially here, you had the task to look at the number of nodes in the simulation. You had to think about the number of lookups which have been initiated in this simulation. What is the hop count of messages that are sent around? Especially here we consider the average of the hop count and the median of the hop count. And we have a look at the overhead in terms of forwarded messages here in the network. So especially we had the question, is there an imbalance here? So I just present you some results, the most important pictures you can find in the simulations output folder. And the first question was related to the number of online hosts in the network. And for this reason you had to change the config file of the simulator, of the chord configuration, and you should prepare the simulation such that churn is started in the 30th minute of the simulation. And here in the first picture you can see the number of online hosts for a given time in minutes. And you see here the initialization phase in which all the nodes join the cord network, the cord overlay. Then the number is stable for a certain time, and then you can see here in minute 30 churn starts, and suddenly most of the nodes or some of the nodes go offline. So you were also asked to inspect the connectivity during the simulation, and what you can see here is the connectivity of nodes that are going online at a specific time or a specific minute in the simulation, and you can see the connectivity of nodes that go offline at a specific time. So I think this both graphics best describe how nodes join or leave the network. And next, we considered the number of initiated lookups in the simulation. And therefore, you had this in the outputs folder. I think it was all the files that are related somehow to the DHT overlay something. And, what you can see here is also the number of initiated lookups. Here we start at, I think, minute 35. Some random lookups were started. We have here the total number of lookups in the simulation, and here we have the number of initiated lookups which are sorted and assigned to the peers here. So what we can see here for how many peers, how many lookups are started. So there are some nodes which have let's say high number of lookups started, and then we have here many peers which have no lookups started. What we can then have a look at is the number of finished lookups. So in the cord overlay there are some mistakes that can happen, that can take place, and if the cord overlay somehow has some problems and this has a malfunction, dysfunctioning, then we see that some of the lookups are not finished. This is described here that the number of all finished lookups is not so high than the number of initiated lookups. So for the hop count, yeah. Yeah, you. Mhm. So it might be that you consider the number of initiated lookups for a certain time. Okay. So, shall I proceed? Yeah. Okay. So just to rush through this exercise here, you can visualize the number of hops for the messages. We have the hop count, the number of forwarded messages in the network. Here again, the global view of forwarded messages, and we have the forwarded messages from sorted to the peers. So let's go through this. You will find this in the solution, and we have the number of total bytes which are sent from each peer, and we have the number of messages which are sent in the network. So your next task was to compare chord and pass-tree. For this reason, you had to start, I think, another config file, which was located in config education in this folder. And the main focus was here on the difference in the messages you send and receive in this overlay. So what you should see there in the simulation is that chord, for example, sends messages around all the time just to maintain. We have a question there. Sorry. Die sollten parallel laufen. Gerne. Okay. Soll ich erst durch das Ergebnis gehen oder soll ich das direkt einmal zeigen? Ja, ich gehe dann einfach mal durch. Zack. Okay, yeah. I will repeat this in English just for the other people here. So the question was how to run different simulations in parallel. Not only one simulation, but 3 or 4 or multiple at the same time. And for this reason we had here the batch runner. I think this one. So what you simply have to do is to maybe type in the terminal, or you can use the scripts here. You use Java, and then you start not the GUI runner or not the simulation runner, but the batch runner. And you can start it with different parameter. So I hope maybe this is right here. Here we have an example. Yeah. So you start Java, the batch runner, and you have here 2 parameters which tell you how many simulations in parallel you want to run. So you can here run 2 different simulations at the same time. So you will start 2 different threads which run the simulation, and in general you want to simulate 4 simulations here in total. So and then as last parameter you tell the simulator, okay, which config file you want to run. So just to show you what happens if I do this. So this is here you can see that different seeds are set and just that you can reproduce your results. So, and then in the outputs folder you see here that different simulations are started with different seeds, and for each simulation you have the specific results of the simulation, and the so the results of this 4 simulations are then collected and gathered and merged together. So here as a result you have then the averages of the 4 simulations. And if you run different simulations with different variables and different parameters, you will have here a merge of these different parameters in the main folder. So I hope your question is answered. And okay. Sorry. Yeah. Maybe, yeah, there are some parameters, some variables you have to set. Yeah. Ja. Das sind diese beiden Parameter hier, die gesetzt werden. Ja. Hier übergibt man dem Simulator mehr oder weniger, wie viel RAM mitgegeben werden soll. Yeah, another question? Yeah, so you can good question. So if you run only one simulation, you can specify the key or the seed you want to use for this single simulation. Yeah, and this seed is set in the config file. But if you want to have multiple simulations in parallel, they shouldn't be all started with the same seed. So therefore, the simulator selects some random seeds which are simulated. Okay. Yeah, another question. Mm-hmm. Yeah, in principle, yes. I'm not sure about it because you have to specify in this config file, for example. Let's say we want to consider chord here, because normally there's only one overlay here, one class you provide as an overlay you want to use. Okay. Yeah. I don't really know. Okay. Okay. So yeah, you have to specify it here in the variable part. So, for example, which kind of overlay you want to use, and then you can override it here in the end. So it would look something like this. For example. Yeah. Okay. Yeah. Here you have different churn values, but you could say here for example we use overlay equals, and then I don't know, chord 1, chord 2, for example. And then here in the file you would have to specify such a variable that you have here the overlay, something like this. And then you would have the value here. For example, you could copy, I don't know, the overlay you want to use here. And then you could say here, okay, class equals overlay. So, and then it should work. Yeah. Mm-hmm. Yeah. So this is the number of seeds you want to use. So this is the number of simulations you want to use, and this is how many threads are run in parallel. The normal simulator, then only one seed is running. This is then the default seed you use in the config file. If 0, for example, if you set it to 0 in the config file. Mm-hmm. It's just a number. Yeah, and you can, for example, here you have the seed here, and you can I don't know, change it, and then you run the simulation with exactly this seed. If you only it is so the random generator inside the simulator is then prepared to use this seed. So all the events that take place have the same results as they have the same random parameters and variables. So okay, back to the exercise here. So again, what you had to do is to compare chord and pastry in terms of messages that are sent around. Again, what you can see is that chord sends messages all the time in the network to maintain the chord ring. And pastry doesn't behave like this. There are no messages which are sent around all the time to maintain the network. And just to simply explain this observation, I have here the solution. In chord, messages are periodically sent around in order to maintain the chord ring and to prevent the overlay from misbehavior. And therefore we call the chord protocol it is a proactive approach. We heard about the differences: proactive, reactive. And pastry, on the other hand, doesn't need to send around messages to maintain the overlay, because it is rather reactive. So whenever a node detects another node to fail, it can react on such an event and change its routing table and, as I said, react on this event. So the third task was then to consider the EduStar overlay, a simple overlay, the star topology. We had one node in the middle, and all the other nodes which connected to this node just sent ping messages to this node and received a pong afterwards. So anyone who wants to show his or her results, otherwise we can maybe directly go into the code and see what should have been done here. So okay. The first task was then to create a GNU plot file for this simulation to show the results. We will put this solution onto the website and also put the GNU plot files onto the website. I show you maybe the results here. Okay. So this is how it would look like. We set the terminal of the output. We specify the name of the output file. We define some labels, and the most important thing here is that we want to plot the edu analyzer dataset using either the second column or the third column for, I don't know, for visualizing the number of pong messages which are sent around, or the number of nodes that are online here. So, and from the last outputs maybe, okay, we have here the script, we have here such an analyzer data set, but we have no plot file, so let's copy this. So let's see what happens if we run the script. Okay. Then here we tested the overlay without churn. So we see the number of nodes in the network is increasing, and then comes to a stable line in the end of the simulation. Sorry. So okay. The task was here to plot the number of nodes in the network, and I think more important here was to okay. If you want to present it, come in front and show me. Okay. Yeah, what we had here is for analyzing we had the edu analyzer. So what you could do here is just to plot the number of nodes in the network. You could introduce such a list, for example, which is here used to store the number of nodes which are online in the network. So nodes which go online or go offline, they have to change this list. They can add their information to the list, or they can remove themselves from the list. And this is done here, for example. Here I used two methods, for example the register node method, in which nodes are added to the list, or the unregister method, in which nodes are removed from the list. So then in the end here we write our all our parameters to the file we want to plot in the end. And here we had the number of pings already written out, and then you just have to add online nodes. This is our list dot size, and this prints out the size of the list. So it is very simple. So, but what you had to do is here, of course, to change the method connectivity changed. It was in the exercise sheet. What you can see here is if nodes go online, for example, they register in this list we have proposed in the analyzer, or they unregister from this list if they leave the network. So it was just two simple changes in the network. So were there any problems with this task, or any annotations? Okay. Yeah. So I think this was part C of the task, and it goes somehow hand in hand. Because if you add here in the analyzer the possibility to count the number of nodes, it is more interesting to change here the behavior of the network to analyze the churn model, to register and unregister the nodes just to see what happens. Okay, and the last part was then to stop and start the operations in case a node goes on or offline again. And for this reason we had here, where is it? In the beginning, the ping pong operation, which is started by every node. So even the node in the middle sends ping messages to itself. Okay, this is just simple overlay. What you could add here is just to store this ping pong operation in your star node class, so that you can, just that you have access in this class here to the ping pong operation, and you can then define simply a method to start or stop the ping pong operation. And how it is done inside the ping operation, I show you now. So what you can do is here just introduce a parameter which is a Boolean value for is the operation active or inactive. And whenever you want to execute the operation, just ask, okay, just check if the operation is active or not active. And the parameter, if it is active, you can set via the start and stop methods. So just be sure that if you start the operation again, that you schedule it again, because otherwise it won't be scheduled in the simulator. Okay. Are there questions? No. Not even from Ahmad. Okay. Okay, you have a question. Yeah, it is correct. If you have no churn, then it is correct, because every time you join the network, you can increase this value and print it out, and then you have the number of nodes in the network. Okay, but then you have a problem. Then you have to consider the churn. So if the node goes on or offline again, then you should increase or decrease this value to obtain the same result. Okay. So then next I want to present you the next exercise, the next task, and I hope in detail, maybe in detail I can show you how to solve the task and where you have to be careful, what you can do. Ah, okay. Ah, okay. Yeah, so I told this, okay. Yeah. Okay. This was part here of the connectivity changed method, yeah. As I told you before, you can register or unregister nodes to the analyzer, and then they are printed out. So if we start such a simulation, yeah. Here, for example, we run the EduStar now. So we have some results here. And let me copy the GNU-plot file into this folder. So yeah. Okay, now we plot here the outcome of the simulation. And what we can see here is then, okay, at first you have all the nodes that join the network, then the number of nodes in the network is stable for a certain time, and then after 30 minutes churn is taken into account here, and then you see the number of nodes decreases slightly in the network. Okay, just to have the visualization. But I hope it is clear how to to write the results into the simulation or in the analyzer file. Okay. So in the next exercise, then we extend the simulator again, and this time we try to implement chord in perfectsim.com. So, or rather, let's say there's a specific skeleton you can use here in the simulator, which gives you a simple implementation of chord, and you have to extend this this packages. So what you should first do is, again, if you haven't done this before, to download the simulator, you should install GNU-plot, and you should install another visualization software called Graffi. You can download it from graphis.org, or you can simply install it by typing in sudo apt-get install Graffi in the terminal. And, this is a tool which helps us in the end to simulate or to visualize the overlay and to see if we have formed a chord ring or not. So for the preparations, make sure that you install this software. You should run the script run edu-chord.shell, which is located in the main folder. And then you find some results in the outputs folder. I show you now how they should look like. So what you find here normally is then a folder called graphs, and you can find here additional files and a script, and if you run the script you can visualize the chord ring, for example. This gives you PNG files or PDF files of the corresponding overlay we have simulated here. And what you can see in this picture, that we have the different nodes which participate in the overlay with their IP addresses, and as this is here a simple chord overlay, we have on the one hand the successor for each node, and we have the predecessor for each node. Here the black arrow is the successor and the green arrow is the predecessor line. Okay. So, yeah, to investigate chord in detail, just make sure that you understand how the protocol of chord works. For this purpose you can read the paper. We have put this into the folder of the new version of the simulator. Then you will find here a folder education, and in this folder you will find the chord paper. Especially part 4 of the paper is about the protocol of chord. There you find the different methods which are used inside of the overlay. For example, how to join the network, how to stabilize the network, so how to distribute the successor and the predecessor pointers for each node. So, and the first task, the first real task is then in the overlay to focus on the find successor method of chord. So the find successor method in chord is just used to find a certain ID in the network, or more or less to find a responsible node for this ID in the network. For example, here we have different nodes, and let's say, okay, there is a certain key which is stored here at this node, or let's say this node has a certain ID, for example 300, and this node is now searching for a node which is responsible for the key 300. Then okay, we have a distributed protocol here, find successor, which which is traversed through all the nodes just to find the position here in the network, and to find the node which is responsible for this ID. Okay, what you first should do is investigate the class chord node in our new overlay package. I will show it in a few seconds, and then you should consider the find successor operation. Okay. As this is just a simple chord implementation, we only have here predecessor and successor pointers, and your task would be then to introduce a finger table, which is used in chord, to this implementation, and to use these fingers to search for a specific ID in the network in the end. So, now I want to go in detail where you can find these parts and where you have to change something. So this won't be the problem, I think, then. So here we have the implementation of a simple chord node. Just let's go through it. So when the node is set up, okay, we have some information we want to store. We want to store on which host is this application running. We want to know about the transport layer, and we want to know about the network layer of the host. And to use the transport layer and the network layer of the host, we have to specify a certain listening event here. So then, as a next step, we create a new chord contact. In this class chord contact, we just store the transport layer information of the node. We store the port of the application which is used here, and at the same time, if we create such a class, such a chord contact, an ID is assigned to the node. How this is done? If we create such a contact, we simply hash the IP address of the node, and then we obtain a chord ID. Okay. So what we typically do then in the next step is we want to join the network. Therefore, we have a Bootstrap manager, which gives us a random node from all the nodes which are already participating in the network. We are asking for a successor in our own network, and if we obtain from the Bootstrap manager so a contact which is null, so this means the Bootstrap manager is empty at the moment, we know, okay, I am the first node which wants to join the network, and so I consider myself as my own successor. This is what we do here. And after this, okay, we say the join operation has been successful, and we can move to the new step. Okay, but if we obtain now another node from the Bootstrap manager, we can use this node we obtained to find our position in the chord network. And to find our position in the chord network, we simply have to execute the find successor operation for this node. So this is done here. We have a new find successor operation, which is directly scheduled at the node. And, what we have to give to this operation is the node class by itself we are using here. Somehow we have to pass over the contact node we have obtained from the Bootstrap manager. And what we are searching for is our own ID in the network, because we want to find our successor, or the successor for our ID in the network. And we pass to this operation a callback. So, but what exactly is a callback? So a callback is typically used here to tell an operation which method or which class should be executed after the operation has been successful or not. So we create a new operation callback. This is just to show you this simple interface with two methods we have to override. And if we override this method, okay, we can say, for example, if we override the method called operation failed from the interface, we can specify what we want to do here in case if the operation failed, or we can specify what to do in case if the operation has been successful. In this case, if the operation has been successful in the end, so if we have found our successor in the network, we can execute the join operation success. So what to do then? Okay, we have then obtained our successor in the network. We should store this successor in our class. We should notify the successor that we are his successor. Then maybe he can consider us as his new predecessor. Then we have already an ordering in the chord ring. We register the node in the analyzer, so that we can tell the analyzer, okay, there's one more node that is online. We want to register ourselves in the Bootstrap manager, so that other nodes which join the network maybe can select us as entry point in the network. And the most important thing here is we start the stabilize operation of the chord protocol. And, the stabilize operation is the most important operation in chord, as it tries to update the successor pointers of the nodes and tries to update the predecessor points upon this event. Okay. So what we do here then is additionally we start some periodic lookups. So this means we periodically create a random key in the overlay. This might be any number, and then we search for this number in the overlay just to see if every number or every key in the overlay is reachable. So as a next important part of the overlay, we have here a simple message handler. So whenever a message arrived at the node, we have to decide what to do with the message. What kind of message is it? Here, for example, we have incoming find successor messages, which are sent from the find successor operation. Whenever a node receives such a find successor message, he should react on this and try to search the successor for given node which sent this message to the node. So, okay. What you would do then is, if you receive such a message, you would try to consider if you are responsible for the searched ID in the network. Then you should answer to the node, okay, yes, I'm responsible for the ID, and I pass my contact information to the node. Or in case if I'm not responsible for this ID, I should pass this ID or the whole message to the successor of myself, so that the successor might be able to search for the responsible node of the ID. This can be seen here. Okay, we start the find successor operation again, and in case if this is successful, we create a new find successor response. So we want to answer this message. What we put in there is our information or contact information. We put in the sender of the first message. So this is contact, so the node we want to inform that we have found a successor. Then we should put the successor we want to send to the searching node into the message. And as a last step here, we calculate the hop count for each message. So we want to know how many nodes does a message have to traverse if we search for a certain ID. So then there are other rather minor important methods here, or messages we can receive. On the one hand, there is a get predecessor message we can obtain. This is simply a request of another node that we should send our predecessor contact information to this node, so that he can stabilize the local information of the chord ring. And we have a notify message which is sent to a node just to inform that there might be another predecessor than we currently have. And as you will see, okay, then we try to update our predecessor if we receive such a notify response. So some other methods. Okay, again we have the connectivity changed method, just in case churn occurs. We have some operations which have to be started or stopped. We have to register or unregister our node from the Bootstrap manager, and we have to register or unregister our node from the analyzer, just to tell the analyzer how many nodes there are in the network. So this was the first task here. should now have we should take a closer look onto the find successor operation. What is typically done here if we start such an operation. So what we do here is first, okay, we create such an operation and then we execute this operation. And the first thing is what we do is we check, okay, is the node itself responsible for the ID we are searching for? So this would mean, okay, the ID we are searching for is in the range of the node itself and its successor. So, okay, then we can deliver the result. We set the result by ourselves. So we create a new response message, and what we put in there in the response message is just our own successor. So otherwise, if the ID we are searching for is not between the node itself and its successor, we try to forward the message to our successor. Then our successor should consider, is his successor responsible for the ID or not, or maybe should the message be forwarded to this. So yeah, then we would create a message in which we have contact information about our successor, about ourselves, and the target ID we want to search for. So what we do then is we send the message to another node, and we wait here if timeouts occur. Just in case a message gets lost, we can react to this. And if a message gets lost, okay, we can resend the message. Otherwise, if it happens more than 2 times here that the message failed, we finish this operation, but here with false we declare that this operation hasn't been successful. In this case we do nothing, because then we have message loss and the message is not there anymore. Okay, but it might be that we then, in the end of the operation, receive from another node a result about a successor of an ID which has been found. So we store this result, which is stored in the find successor response by itself. In this message we store the successor and the hop count of the traversed messages, and then we finish this operation with the additional parameter true. That means, okay, our operation has been successful, and in the end we can obtain the results via this method here, get result. So this is only the one part of the operation. This is only the sending part of the operation. So this is only the part when another node wants to search for a successor in the network. The other part is then, as I told you before, what happens if I receive such a message, such a find successor message. Then I would either I would be responsible for the ID. Then I would tell the requesting node, okay, I am responsible for this ID, and I give you my contact information. Or otherwise, if I'm not responsible for the ID, I would forward the message to other nodes, to my successor. Just to give you a little hint how to put in the finger table here as a task. Okay. First, you should specify somehow how to store the finger table, so there should be more than one contact information for the finger tables, because you have here more than one fingers. I think here it will be 160 fingers. Okay, you should store them somehow, and then you should here change the find successor operation in that way that you consider even the finger to forward messages. So messages shouldn't be forwarded via the successors only, or they should forward it as far as possible into the chord ring. So, and this is typically done by considering the finger, for example, the closest preceding finger, which is the best new contact information for reaching a desired target ID. So what you should do then is here to take into account that you forward a message not only to the successor, but also here to a finger. And, in the chord paper by itself you will find how to calculate the finger table, how to calculate a finger for a given ID, and I think it is very easy then here just not to use successor but something like finger, I don't know, get trans information. And then you can use this finger instead of the successor. Okay. So then, as a next task, you should investigate how does your overlay behave then if you use fingers instead of your successors only. And, okay, this I give to you. What we have here is that we obtain in our results the number of hops a message has to traverse if you find, or if you try to find an ID, if you search for an ID. And what you should do now is then, okay, just think about how should the number of hops change if you use fingers instead of the successors only. Then as a last step, we consider churn now under chord. You should simulate the given chord implementation with churn. Currently it is simulated without churn, and you should see what happens there to the protocol. And what you should see then is that the chord ring is somehow broken, and that you have for some nodes no successor pointers, no predecessor pointers, so there is somehow a cut in the chord ring, and a cut in the chord ring. So for this problem you have then with the chord ring, you should find a solution, and you will find this solution in the chord paper. You have to read carefully part 4 of the paper, and you should then implement the proposed solution of the paper, so that in case of churn you find some other contact nodes which can be contacted if you want to search for an ID, if you want to send messages. The ring is not corrupted anymore, and that you have one global chord ring which is fine, which is has no failures, and where everything is correct. Do you have questions so far? I think this was pretty much, but I think you have a lot of time to solve this task and to get into this task. Yeah. Okay. Then if there are no questions, I think I'm finished. Here, yeah. I don't really know.